Agents are non-deterministic. That's a problem for real life. Now, really think about that for a second. I mean, we've all seen those incredible, highly polished demos online, right? The ones where an AI agent flawlessly executes this massive, complex string of tasks in perfect sequence. Honestly, it feels like magic. But as soon as you take that exact same agent, deploy it into production, and hand it over to actual customers operating in completely unpredictable environments, well, everything changes. That unpredictability, that inherent non-determinism, where the exact same input might give you a slightly different output tomorrow, is a massive hurdle. It is literally the core challenge we have to solve if we ever want to build reliable, enterprise-grade systems that actually drive value, instead of just total chaos.
So, welcome to this explainer. Today, we're taking some seriously deep technical insights from Microsoft's engineering teams and transforming them into a highly structured, step-by-step guide for building, evaluating, and securing production-ready AI agents. Look, if you want to stop constantly putting out fires in your AI applications and finally get ahead of the curve, you are absolutely in the right place. We're moving completely past the conceptual hype today. We're focusing entirely on the hard truth, how you actually observe, troubleshoot, and optimize these complex multi-agent workflows when they're out there operating in the wild. Here's our roadmap for today. First up, minding the agent gap. Second, the observability framework. Third, evaluating quality and safety. Fourth, tracing and red teaming. And finally, number 5, automating the optimization loop. Let's get right into it. All right, Section 1, minding the agent gap. If you've ever ridden the London Underground, you absolutely know the warning echoing over the loudspeakers, mind the gap. It turns out this is the perfect analogy for agent development. Think of the platform as your rigid developer requirements. You know, the strict business logic, the compliance rules, your brand voice guidelines. Those things are immovable. They absolutely cannot change. The train, on the other hand, represents your AI agent in motion. Now, in a perfect world, like a perfectly controlled demo, the train stops totally flush with the platform. But out in the wild, as models evolve, as prompts change, and as users start throwing completely bizarre edge cases at your system, the agent's behavior subtly shifts. Suddenly, a dangerous gap opens up between what you rigidly require and what the agent actually does. Minding that gap means putting the right observability tools in place so you can instantly detect the exact moment your agent starts drifting away from its instructions. To ground all these abstract concepts, we're going to follow a specific real-world developer journey throughout this explainer. Let's imagine you've just been tasked with building the Contoso travel agent. This is a fictitious app designed to help real users seamlessly orchestrate flights, hotels, and car rentals. Now, you aren't just slapping together a simple chatbot here. You're designing deep, specialist agents for each individual travel component, and then a master concierge workflow agent to knit them all together. Managing the gap in this kind of environment is absolutely critical. Why? Because if just one specialist agent goes off the rails, say the car rental agent hallucinates a booking, the entire cascading workflow collapses, and your user's trip is completely ruined. Moving right along to Section 2, the observability framework. You've got to build observability across 3 distinct, overlapping phases. And this is crucial. It is not something you just tack on right before launch. Bolting observability on after deployment is a guaranteed recipe for massive blind spots. In Phase 1, build and evaluate, you have to embed metrics from the very first prompt you write. You need to assess your baseline quality before you ever touch production. In Phase 2, debug and monitor, you deploy in-production tracing, so you can actively watch the live paths and decisions your multi-agent workflow is taking in real time. Finally, in Phase 3, optimize and fleet-wide control, you step back to manage telemetry across potentially thousands of simultaneous multi-agent systems. You then continuously loop those aggregate insights right back into improving your core codebase. Now, why do you need this structured observability so early on? Well, get this. It's because of the frankly overwhelming volume of choices at your disposal. There are over 11,000 foundational models available on the Azure catalog alone right now. Over 11,000. If you don't have a framework in place from day one to measure performance, you have absolutely no systematic weighted baseline which of those models is actually the right, cost-effective fit for your Contoso travel agent. You wouldn't be engineering at that point. You'd just be wildly guessing. Which brings us to Section 3, evaluating quality and safety. We really have to completely shift our mindset here. We are no longer just checking if the AI speaks well. Traditional model evaluation checks basic things like fluency and coherence, essentially asking, did the model generate a grammatically correct, readable sentence? That was perfectly fine for simple chatbots. But agentic evaluation has to be so much more rigorous. We are handing over the keys to the car. So we have to assess if the agent successfully resolved the true intent behind a messy user prompt. We have to verify if it selected the exact right operational tool from its toolkit. And most importantly, we have to measure overall task adherence, meaning from start to finish, did it actually complete the complex multi-step workflow it was assigned without making things up or just giving up? Let's look at exactly how this plays out for our Contoso travel agent. Say a user types, I want to plan a trip to Paris. First, we evaluate intent resolution. Did the agent correctly understand that this is a travel booking query and not just a request for the weather in France? Boom, success. Next, we evaluate the tool call. Did it successfully trigger the backend flight search API, or did it fail and try to hallucinate a fake itinerary? Finally, the overall response. If the user asked for a trip in September 2025, did the agent output completely accurate, grounded dates, or did it spit back a hallucinated date from 2024? Every single node, every single decision branch needs its own specific evaluation metric. But, simply knowing that an evaluation failed somewhere isn't enough if you don't know why it failed. This is exactly where trace-linked evaluations swoop in and save the day. By linking your evaluation metrics directly to the agent's execution logs, or its traces, you drastically shrink the time between detecting a weird anomaly and diagnosing the actual root cause. Imagine your task adherence score suddenly drops on a Tuesday because you swapped in a new, cheaper foundational model. Your trace-linked evaluations allow you to instantly compare the new execution trace against the old one. You can visually pinpoint exactly which tool call got skipped or misinterpreted. That saves you hours, if not days, of frantic manual debugging.
All right, Section 4, tracing and red teaming.
So evaluating for standard quality assumes your users are acting normally and just want to book a flight. But what about when they aren't? What happens when they actively want to break your system? If standard quality evaluation is like a building inspector coming by to check if your plumbing is up to code, red teaming is entirely different. Red teaming is like actively hiring a professional cat burglar, handing them the blueprints and saying, please try as hard as you can to break into my house tonight. You are proactively using a secondary AI system to aggressively attack your primary AI system. The goal is to expose all the hidden, terrifying vulnerabilities before bad actors out in the wild can find them. And trust me, this is vital because malicious actors use incredibly creative, sophisticated strategies. They might use prohibited actions, trying to logically trick the agent into bypassing its own strict rules, like asking it to leak proprietary pricing data by pretending to write a fictional stage play. Or they might use leet speak, intentionally replacing letters with numbers and symbols to sneak toxic commands right past your standard text-based safety filters. Even more dangerous are crescendo attacks. These are wild. It's a patient, multi-turn approach, much like a frog sitting in slowly boiling water. The attacker asks a completely innocent question first. Then they slowly build upon it, turn after turn, subtly manipulating the context window until the agent is completely confused and executes a harmful task before the system's safety triggers even realize an attack is happening. Let's bring it all together in Section 5, automating the optimization loop. Traditionally, finding these deep vulnerabilities and actively fixing them meant forcing your engineering team to manually write complex KQL queries, that's Kusto query language, just to dig out the data. It meant sifting through massive, unreadable log files by hand, tweaking code in your SDK, and running clunky batch evaluations. It's an incredibly slow, painful bottleneck. But the paradigm has completely shifted. Now, you can actually leverage AI to evaluate and fix your AI. By using a coding copilot equipped with a specialized observe skill, you can literally ask an AI agent to look at your blank Contoso Travel Agent endpoint, and it will automatically build the entire robust observability loop for you in a fraction of the time. This automated optimization loop is practically magic to watch. You turn the coding agent loose, and step 1, it generates its own custom, highly challenging test data based entirely on your unique instructions. Step 2, it automatically runs a massive batch evaluation against that data to pinpoint exactly where your travel agent is failing. Step 3, and this is the absolute best part, it deeply analyzes the reasoning behind that failure, and it actually rewrites and optimizes your system prompt for you. Step 4, it automatically reevaluates that brand new prompt against the baseline, assigns it a new version number, and compares the scores. It just autonomously iterates back and forth, fixing regressions until it hits the highest possible task adherence score, leaving you to simply review its reasoning, verify the safety, and hit deploy. So as you build more complex, capable multi-agent systems, the gap between what you rigidly intend your agent to do and what it actually does under pressure is naturally going to widen. But continuous trace-linked observability isn't just a best practice anymore. It is quite literally your only way to keep your agents safely on the tracks as they encounter the unpredictable, messy reality of the wild. So take a hard look at your own workflows. Are you truly evaluating intent and end-to-end task adherence, or are you just checking for basic fluency? Have you aggressively red-teamed your tools to find the cracks? Because once your AI is out there in the real world, you absolutely must mind the gap.